So we're next going to build on the concepts that were introduced in discussion of Gaussian optics in the paraxial approximation, where everything is nice and easy and simple, and ask how does that change when you switch to a high NA objective where the paraxial approximation is no longer valid and more complicated expressions relate the local electric field within the focal plane with the polarization states that are introduced and detected in the far field. Okay. And we're going to limit this to the case of thin samples relative to the depth of field, such that we still have a point source or a plane wave source effectively for the nonlinear optical response. Okay, so before we get into the nuts and bolts equations, it makes sense to ask why is the polarization state in the focal volume different than the polarization state put in? And the easiest way to look at this, I think, is just get a conceptual framework is just plain geometry. Let's say I've got light that's polarized with along the, let's see, that'd be negative x direction if this is x and this is z. So it's polarized in the negative x direction, and when we tilt at a high angle, then the polarization has some interesting things associated with it. First of all, you can see that it has a z component that was absent before because we're angling that polarization for each of the rays that ultimately all converge onto this point in the focal volume. And you can also see that they're going to have to do some funky things in the focal volume in terms of how they add, and where they add in this region is going to be different depending on where you're looking. So the nature of the position of the sample will also dictate the polarization state within the focal region. It's a little bit harder to see what happens if you look for the orthogonal polarization, but it does actually change the polarization state some as well. So if we look from the top of this objective down, then along the z-axis there's a focal plane there. And if I am coming in with light that is polarized this way, then when I focus it down this line, there's a rotation to the polarization state as well. So there's the angle, the polar tilt angle that results in a z component, but there's also this rotation that mixes the x and the y terms. And so you have everything turning into everything when you start focusing with a high NA objective. So that's sort of the physical picture in your mind's eye to describe why you have this crossing, this mixing between the x, y, and z electric field components, such that even if you put in purely horizontally polarized light, you still are going to get both an x and a y contribution as well as a z just from that one horizontal polarization component. And we can build this up with a 3x2 matrix, which should be straightforward. We know we have to have a 3x2 matrix because we have 3 electric field components at the interface and 2 electric field components for the Jones vector. So we know they must be related by a 3x2. The 3x2 is derived by calculating these I functions, which are in turn dependent on integrals over Bessel functions. The good news is that they converge to let's see, 1, 0, 0, 1, 0, 0 in the limit of a nice Gaussian beam, in the limit of low NA. So we have this relationship where we've got E in the local frame as a vector is related to the laboratory frame Jones vector through this matrix. And this is just a 3x2 matrix G. It does depend on now all 3 angles in spherical coordinates, the position away from the focal point, the azimuthal rotation angle, as well as the displacement along the optical axis. But again, as long as you know where your sample is relative to that focal volume, or for example, if you know it's in the center of the focal volume, then that's a determined matrix. We can calculate all 6 elements of that matrix by evaluating these integrals and just plugging and chugging. So it's a known vector, or I'm sorry, known matrix. Now, in fact, we really want to do is put this G over here so that we can isolate the laboratory frame on one side and then put this matrix over on the other. Now, unfortunately, it's not trivial to take the inverse of G. We can't. When it was just a simple truncated identity, it was really easy to figure out what to do with it to put it on the other side. Now we can't, but we can still just do it numerically. So we can still calculate this such that If we invert it, and oop, hey, what are you doing? Instead of the G, we replace it with gamma, which is effectively the inverse of G, but calculated by G transpose G inverse multiplied by G transpose. So that's what gamma is. But again, it's just like G, it's entirely deterministic. As long as we know where in the focal point we're looking, we can just calculate that matrix. And gamma is a 2 by 3 matrix instead of a 3 by 2 matrix. But each of them is known. Okay, how do we then build these known matrices in gamma into this linear algebra architecture that we've been building up the whole time for relating the local frame tensor to the Jones tensor, which we then in turn relate to the experimental observables. Within the paraxial approximation, just to remind ourselves, we had two things we had to take into account. Well, three actually. We had to take into account the local field correction factors, which are have already been addressed in a previous one and often can be neglected because the local dielectric constant is fairly similar in many media. Not to confuse, I'll caution you not to confuse the local field corrections in L, which with the math that we're describing here relating the local electric field relative to the external electric field. This equation here holds irrespective of if this is done in vacuum or in some dielectric medium. It's just the geometric correction to account for the local electric fields within the focal volume. So in the paraxial approximation, this correction to account for the absence of significant curvature connecting the laboratory frame to the local frame, it's just a truncated identity. All we do is the exact same mathematical architecture we had before, but instead of this truncated identity, we plug in our gamma. Assuming it's in the focal volume, we can calculate gamma identically, and it's a known matrix, so we just propagate for each of these different elements. Two cautionary notes. The first is that this correction depends on where you are. So if you're right in the focal volume, you're going to have one value of gamma corresponding to all three angles equaling 0. But if you're someplace else, you're going to have a different value of gamma, and a different value, and a different value, and a different value. And in fact, you could, and well, oh, come on, stop that. In general, you'll have all of these contributions interfering collectively in the macroscopic response. That does make it kind of a pain in the ass to do the polarization analysis if you have multiple sources all simultaneously contributing. There's two obvious ways to move forward with it. The first is to avoid having that happen. Just choose samples that don't introduce out-of-plane contributions. The other is to introduce scattering components in the sense that these other contributions will be incoherently added to the signal that we generate in the focal plane, and that's exactly the topic for the next discussion on Mueller tensors and Mueller transformations. Finally, the other cautionary note is that there is a difference in the cone angle when you double the frequency, and such that there's a square root 2 reduction in the cone angle for the doubled frequency relative to the fundamental in second harmonic generation. And the reason one understanding that you can hopefully develop to explain this is if you consider, for example, a Gaussian distribution in tilt angles associated with a Gaussian profile illuminating the back of your objective, then with a mean of 0, then this would be the distribution, the probability of having any particular value for your tilt angle relative to this reference. Now for second harmonic generation, we're going to take this whole thing and square it. And that gives you this expression here. There should be an equals here, my apologies. And if we square it and then pull it out, well, if we square this, factor of 2 goes into the exponential and it shows up right here. Now we can fold this 2 into the definition of our 2 theta. Well, actually, well, let's not do that. That's just that, right? And so if we could fold this factor, if we take the square root of it, then we can fold it inside this parenthetical. And now whatever is in here is our new value of theta 0 to omega. And this is exactly what satisfies that relationship right there. It's just off by a factor of root 2. There you go.